In a groundbreaking discovery, scientists have detected gravitational waves from a collision between a neutron star and a mysterious object lying within the so-called mass gap. This event, captured by the LIGO, Virgo, and KAGRA detectors, marks the first observation of its kind, challenging our understanding of stellar remnants. This cosmic encounter not only deepens our knowledge of the universe's most dramatic phenomena, but also introduces us to mass gap objects. We'll explore the technologies that made this observation possible, the significant implications it holds for physics, and what it suggests about the unknown aspects of our galaxy. Join us as we unpack the mysteries and significance of this rare cosmic event, shedding light on the dark corners of the universe. The tale of GW230529, the mysterious gravitational wave event, begins deep in the fabric of space-time, where the most violent celestial dances occur. Detected by the laser interferometers of LIGO, Virgo, and the newly joined KAGRA, this event marked a seminal moment in the field of astrophysics, capturing the first-ever interaction between a neutron star and a so-called mass gap object. Gravitational waves, the ripples in space-time predicted by Einstein's theory of general relativity, are produced by cataclysmic events such as black holes or neutron stars spiraling into each other. These waves travel across the cosmos at the speed of light, carrying with them information about their origins, the nature of gravity, and the fundamental structure of the universe. The detectors, LIGO in the United States, Virgo in Italy, and KAGRA in Japan, operate by measuring the minute disturbances these waves cause when they pass through Earth, using lasers and mirrors spread over kilometers. The signal, GW230529, was first identified in May 2023 and presented a unique challenge to scientists. The waveform patterns detected were unlike typical signals from known binary black hole or neutron star mergers. This prompted an intensive analysis involving sophisticated algorithms and models to decode the signals. Scientists painstakingly separated the noise from the actual data, a process akin to listening for a faint whisper in a storm. The analysis revealed that one of the merging objects was a neutron star with a mass approximately between 1.2 and 2 solar masses, which fits well within the expected range for such stars. However, the other object, with a mass estimated between 2.5 and 4.5 solar masses, posed a greater mystery. This mass range places it within the lower mass gap, a region where objects are heavier than the heaviest known neutron stars but lighter than the lightest black holes observed through electromagnetic means. What makes this detection extraordinary is not just the identification of the objects involved, but the precision and coordination required to capture such an event. The upgrades to the sensitivity of LIGO, Virgo, and KAGRA have been pivotal. The discovery heralds a paradigm shift in our understanding of the life cycles of stars and the remnants they leave behind. This observation challenges several established theories and opens new avenues for research in astrophysics. Firstly, the existence of a mass gap object paired with a neutron star in a merger scenario provides direct evidence that such objects are not just theoretical, but real, and can participate in some of the universe's most dramatic events. This finding is crucial because it fills a previously observed void in the mass spectrum between neutron stars and black holes. The standard theory of stellar evolution suggests that stars with a certain mass range end their lives either as neutron stars or black holes, with a supposed gap in between. The implications for stellar evolution are profound. The mass gap object likely formed under conditions that are not well explained by existing models of supernovae, which are the cataclysmic explosions marking the death of massive stars. This anomaly suggests alternative evolutionary pathways for stars, perhaps involving unusual supernova mechanics or novel forms of stellar collapse. Each scenario needs to be explored further to integrate these findings into the broader framework of astrophysics. Moreover, this discovery has significant implications for the theory of compact object formation. It challenges the clarity of the distinction between neutron stars and black holes, suggesting a continuum rather than a clear division. This blurring of categories compels astrophysicists to reconsider some fundamental aspects of how matter behaves under extreme densities and gravitational forces. The gravitational waves emitted during the merger also provide unparalleled insights into the properties of dense matter and the behavior of gravity in strong field regimes. These observations allow scientists to test the predictions of general relativity in conditions that cannot be replicated on Earth or observed directly through electromagnetic means. As such, each gravitational wave detection enriches our understanding of the fundamental forces that shape the cosmos. As we peer deeper into the cosmos with our advanced gravitational wave observatories, the future of astronomy looks brighter than ever. The detection of GW230529 is just the beginning. With the enhancements made to LIGO, Virgo, and KAGRA, the next observational run, set to begin in April 2024, promises even more discoveries that could revolutionize our understanding of the universe. The increased sensitivity of these detectors means that we can expect to detect gravitational waves with greater frequency and from events further away in the cosmos. This expanded range will likely uncover more mass-gap objects, providing a clearer picture of their role in the universe and helping to populate what was once thought to be a desolate region in the mass spectrum. Moreover, with each detection, we refine our models of how gravitational waves propagate and interact with the fabric of space-time. This ongoing refinement enhances our ability to pinpoint the origins of the waves more accurately, thereby mapping the distribution of black holes, neutron stars, and other exotic objects across the galaxy and beyond. These mappings contribute significantly to our understanding of galactic evolution and the dynamic processes that govern the cosmos. The potential to observe more mergers involving neutron stars and mass-gap objects also holds the promise of detecting new types of signals that could reveal the properties of matter at nuclear densities. This is pivotal for nuclear physics, providing insights into the behavior of matter under conditions that cannot be achieved in any laboratory on Earth. The field of gravitational wave astronomy is on the cusp of a new era. With continued advancements in technology and methodology, coupled with a growing international collaboration, we stand ready to explore the unknown, answering age-old questions about the nature of the universe and perhaps posing new ones. As we gear up for the next observing run, the excitement within the scientific community is palpable, driven by the certainty that what we discover next will continue to astound and inspire us all. Thank you for joining us on this incredible journey through one of the cosmos's most thrilling discoveries. We've explored the groundbreaking detection of gravitational waves from a neutron star merging with a mysterious mass-gap object, a finding that not only challenges our understanding of the universe, but also expands it. This landmark observation underscores the power and potential of gravitational wave astronomy to uncover the secrets of the most elusive celestial objects. Your interest and curiosity make these explorations even more rewarding. Please don't forget to like, share, and subscribe for more fascinating insights into the universe. Thank you for watching and see you in the next adventure into the unknown.